Welcome to class. In this video, we're going to take a look at a cool shortcut for solving linear equations. While we're on the topic of first-order linear differential equations, I thought I would show you a neat trick for actually finding those general solutions even quicker. In fact, many courses don't cover variation of parameters as a technique for first-order linear differential equations. They just show this, but I feel like seeing the variation of parameters helps this to make a little bit more sense. And the trick is to use what we call an integrating factor. What do I mean by that? Well, an integrating factor is just some fancy special contrived function that you would multiply on both sides of your equation to make the problem easier to solve. And it turns out for that linear first-order ODE here, the integrating factor I would choose follows this formula, that e to the integral p of x dx that kept showing up in our variation of parameters. Take a look at what happens. If you recall from the last video, as we were developing the formula for the particular solution, we've actually already seen that the derivative with respect to x of mu times y, the mu being the function I've defined here, well, I take the derivative of mu with respect to x times y plus mu times the derivative of y with respect to x. And we saw in the previous video that d mu dx is actually just mu p of x y plus mu dy dx. Why do I care? If I look at, so here's a little bit of a thought cloud, I guess you could say. Here. Now it's a thought cloud. If I start from this equation and I multiply both sides by my integrating factor, do you notice that I get mu dy dx plus mu p of xy equals mu q of x? Well, this whole left-hand side is just the derivative of mu y, which is mu q of x. So now we can actually solve this in a single integral. I think it'll be easier to see with a particular example, though. So let's check one out. So here's one for us. Let's solve x squared minus 9 dy dx plus xy is 0. The game plan is going to follow exactly what we did over here. It's just that now that I have a real problem, I can finish off this integral in a way that's a little more relatable. So first things first, all of these formulas, again, are dependent on my equation being in standard form. So let's start there. Remember, that just means that my first derivative should have a coefficient of 1. So in this case, I need to divide everything by x squared over 9. And I get dy dx plus xy, or maybe I'll write it x over x squared minus 9 times y equals 0. And now it's a little bit easier to tell that this is linear. Here's my p of x from my formulas. This would be q of x in my formulas if I were using my variation of parameters method. But instead, I want to do the integrating factor. So I build the integrating factor by letting mu be the function e to the integral x over x squared minus 9 dx. Using a u substitution and some laws of exponentials, you should arrive at the square root of x squared minus 9, being our integrating factor. So now, according to over here, our game plan over here, is I just multiply through on both sides of the equation by that root x squared minus 9. So I get root x squared minus 9 dy dx plus, I've got a 1/2 power over a 1 power gives me a negative 1/2 power, or x over root x squared minus 9 y equals 0. And you can verify this product rule for yourself, but this whole left-hand side actually just ends up being the derivative with respect to x of my integrating factor times y. Now all I do is I integrate both sides. And I want to show you one extra step to make this a little bit more clear. I can rewrite this equation. Again, you can almost think about abusing the notation and multiplying the dx over to the other side. But really I have that this stuff equals 0 dx. And now it's a little bit more clear when I integrate both sides. If you think about this as your variable, the antiderivative of 1 is just the variable, right? Which is root x squared minus 9 times y. And of course the integral of a constant, of 0 is just a constant. Last step here is that I should isolate y for my general solution. And as a fun exercise, I would recommend that you try, after this video, using variation of parameters to see if you can get the same answer.